Hello, everybody, and welcome to today's group meeting talk. Today we have Bruno Torres. Bruno, can you share your screen?
Yeah.
Bruno is going to talk about a comparison between the Fuster-Birch and the under-the-wind frameworks or detector model frameworks for measuring quantum fields. And some particular application we will focus on is when can weakly coupled detector harvest entanglement? Bruno, the floor is yours.
Thank you, Eduardo, for the introduction, and thanks everybody for being here. So as Eduardo was saying, we're going to be talking about an analysis between two frameworks for measurement theory in QFT that have motivated a few discussions in the recent past. And in particular, what I'm going to be talking about here is going to be based on work done in collaboration with Daniel Grimmer and Eduardo Martinez. So the outline of the talk is pretty much divided like this. So the first half would be mainly a setup for the motivation of what we'll be discussing. So both from the side of the general aspects of a measurement theory and quantum field theory, as well as a review of this algebraic quantum field theory approach to measurement problem that's encoded in the Fuster-Birch framework and the Rubak model, which is a concrete realization of one particular toy theory that is formulated in the language of the Fuster-Birch framework. And as we'll see, some conclusions that were obtained in particular from one of these recent papers motivate a more careful analysis on those aspects and how they impact the conclusions that we can draw for realistic detector models and real experimental setups. So useful references for the material I'm talking about can be summarized like here. So the Fuster-Birch framework is summarized in this paper here that was published in 2020, quantum fields and local measurements, that sets up the framework more generally. Then this is the paper that, in a way, we're kind of responding to, which makes some more specific claims about the entanglement harvesting protocol for local particle detectors within the framework of the Fuster-Birch approach. And this is, as I was saying, the paper that we've been working on and should appear on arXiv soon. Right? So yeah, the general motivation, as I was saying, has to do with this approach to measurements in quantum field theory. So as we all know, quantum field theory is the best framework that we've been able to come up with, where we can describe the most fundamental theories for the elementary interactions that we know of. That's like the interaction of the standard model. Gravity is a bit more complicated, but still, quantum field theory has a range of applicability that covers several topics in fundamental theoretical physics, such as high energy physics, which is where you usually hear about it the first time, but also condensed matter and applications in cosmology, in quantum field theory, pure spacetimes, and so on. But what is a bit surprising is that until fairly recently, I think we can argue that little was known or even discussed about how to conceptualize measurements within that framework, in particular in a way that's consistent with the underlying principles of the theory, such as locality and causality and so on. This has become a more active topic of discussion in recent years, and one of the consequences of that, I would say, is this field of relativistic information, which more generally is interested in relativistic aspects of quantum information tasks in scenarios where relativistic effects are important, of course. And one pretty basic question that is very much active in this area is exactly the notion of how to make sense of measurements in quantum field theory. So in non-relativistic quantum mechanics, like in undergraduate quantum mechanics, as we first learned, the elementary tools and concepts that we use in order to talk about measurements are fairly well understood, right? That's when you hear about the Bohr's rule and projective measurements, and then in more sophisticated approaches, positive operator value measurements or measures or POVMs, Luder's update rule, and so on. And also in these circumstances, the kinds of physical setups that we have in mind are such that there's no controversy as to when each of these concepts is to be applied and how they work, right? But in relativistic settings, particularly when we have quantum field theory, the situation becomes a little bit more complicated. And just to say, one of the most immediate problems you come across is the fact that the very notion of projective measurements or projector valued measures is inconsistent with the most basic ingredients that define a relativistic quantum field theory, such as relativistic locality and causality, right? So the way that we like to talk about this, or the way that we like to solve this problem, is through these notions of particle detector models, which, as we all know in this group, they should be understood as localized quantum systems whose internal dynamics is effectively non-relativistic, so that the usual postulates for the measurement theory on non-relativistic quantum mechanics apply to a very good extent in these setups. And we are using those non-relativistic quantum systems as probes that couple to the quantum field of interest, right? So they're going to couple through some interaction, of course, in the most, in the simplest setups. For example, that we like to talk about the Unruh-DeWitt model, for example. You can describe them in terms of an interaction action that looks like this, where phi is the quantum field of interest here, a real scalar field. Mu is an operator in the Hilbert space of a detector. So you can think about it as the monopole operator on a two-level system. Or you can also think, for example, in a harmonic oscillator case, as the position operator. But the important thing is that this should be an operator that acts within the Hilbert space of the detector and generates transition between its energy levels. And as lambda here is a space-time scalar function that localizes the interaction around some well-defined trajectory in space and time, right? Now, this kind of framework or this strategy to make sense of measurements in quantum field theory in terms of measurements on the probes that indirectly affect the field has been very powerful and very useful from a variety of reasons. First, it is an effective way to approach from a very operational level the several fundamental effects in quantum field theory, such as the Unruh effect, for example. It also has been shown to yield a full measurement theory for Q of t, which has all the nice properties that we expect a measurement theory to have. So it has a state-of-day rule. It's able to account for single-star experiments, and it's also consistent with the underlying principles of the theory to the best of as best as we can. And it also connects in a very straightforward way to potential experimental implementations and realizations of these models with setups that can be found, for example, in quantum optics or superconducting qubits and stuff like that. But there's a problem, right? That because the model hinges on this assumption of some non-relativistic system that couples to the quantum field, the ability for it to be phrased fully in the framework of a relativistic quantum field theory is compromised, right? We are taking for granted that we can talk about some non-relativistic system in order to be able to talk about everything else. So some people decided that it was interesting, and I agree it's true, to think about how to address that more fundamentally, let's say, completely within the axioms of relativistic quantum field theory. And that's exactly what the field-server framework aims at doing. So we're going to review a little bit of the ingredients that comprise the field-server framework right now. So as we have been saying, the field-server framework is the most rigorous formulation of a setup for a measurement theory in quantum fields, because it is phrased in the most rigorous language to define quantum field theory itself, right? So it is fully phrased in terms of algebraic quantum field theory, and the basic ingredients of algebraic quantum field theory are the following. First, you have some differentiable manifold with a Lorentzian metric. So resulting in a globally hyperbolic spacetime. So this can be any possibly curved spacetime that you want, as long as it is globally hyperbolic. And the reason why you want global hyperbolicity, some of you may know, and we're going to come across it in a second. Then you have an algebra of observables that you should think of as basically the field operators, or the field degrees of freedom that live across spacetime, with some technical assumptions here that give you this notion of a star algebra with some unit elements. So that's the unit of star algebra requirement here, along with a collection of substar algebras for every subset of this manifold. And as I was saying, this should be thought of as the restriction of the full algebra to some local region. And also, to complete, we have to define some notion of states, so some prescription for states, which in this case are just abstractly defined as maps from the algebra to the complex numbers in this case. So the way to think about it is roughly that this takes operators or observables on the algebra to their expectation values. So yeah, these are positive, which means that they take positive semi-definite elements of the algebra to positive numbers, and they're normalized, which means that it takes the identity to 1. Right? So yeah, as I was saying, the algebra together with its collection of subalgebras defines this local algebra of observables. And the fact that we're dealing with relativistic quantum field theory imposes some additional constraints on what properties this algebra must have. The first one of them is isotomy. So basically says that if a region in the manifold is contained in another region, then the algebras are contained in the same way. Then compatibility basically means that if you take any subregion of the full manifold and you think of this subregion as a manifold in its own right, the algebraic quantum field theory defined in this submanifold is the result of the restriction of the bigger one to the subregion, which is pretty reasonable as well. The time slice property means that the algebra of a region is the same as the algebra of any region whose domain of dependence includes that first region. So in particular, this means that your theory has a initial value formulation that can be phrased in terms of a dynamical law. So in particular, if the spacetime is globally hyperbolic, the full algebra is contained fully within any region that contains a Cauchy surface for the spacetime. Einstein causality is the most important requirement, I would say, for relativistic quantum field theory in particular, because that is the one that places the no signaling requirements in a way. It implies that if two regions are causally disjoint, so there's no causal signals that can be sent from one to the other, then all elements of the local algebra in one region commutes with all elements in the other. And there's also a fifth one that's harder to put in words. I'm just adding it for completeness here. It's called Higg property, and it basically says that in a way, the algebra contains all the degrees of freedom that are relevant for the physical theory you have at hand. So yeah, so all the theories that we're going to be talking about, both for the probe and the target system, as we're going to be calling it, should be understood as these in the algebraic sense. And then the measurement setup is going to be phrased as you having a target system, a probe theory, and a couple theory that is the collection of both, right? And the coupling between the target and the probe is then going to be localizable to some coupling zone, which you should think of as the region where the interaction takes place or the coupling takes place, right? And the fact that this third theory, this couple theory, is really a couple version of the target and probe is formally introduced by postulating the existence of a map between the two algebras, these algebras being decoupled algebra here, the couple theory, and the simple tensor product algebra of the system and the probe for any region outside of the coupling zone, basically. Here it's the causal hole. Technically, the causal hole is basically the smallest globally hyperbolic submanifold that fully contains the coupling region. So this is just a technical requirement. You can basically think of it as roughly saying that outside of the coupling zone, the coupled theory and the simple juxtaposition of the two, the system and the probe, are isomorphic to each other. The existence of this isomorphism can be shown to lead to a map from the uncoupled theory to itself that gives a scattering map. So, and this is really a version of something like the time evolution operator in the way that we are usually formulating it in Arduino models, or the scattering map, or some S matrix kind of thing in quantum field theory, the high energy physics setup. And then once you have initial states for the probe in the system, this scattering map allows you to define implicitly an update for the final state of the probe after interacting with the system that is defined implicitly by this equation here. So you basically define a state through its expectation values, or how it produces expectation values on elements of the algebra. And the updated state is defined by this requirement for all the elements of the algebra of the probe, right? Now, in particular, we want to look at the case of entanglement harvesting, which basically consists of you having two separate probes. So you have probe theory that now consists of two independent probe fields, and the coupling will split in two regions. The probes will be initialized in separable states, and the target system will be initialized in another third state, so the full system is in this product state. You're going to send this through the scattering map, which will give an updated state for the uncoupled theory. And then you're going to verify the entanglement on this final state of the probes. But in particular, in this case, you also require that this entanglement will only be tested, let's say, in two localized processing regions. So those are the two regions where you're gonna test if the two algebras are entangled from probe A to probe B. So the schematics is roughly like this, right? So you have a coupling region for a probe A, a coupling region for a probe B, and processing regions to the causal future of both, right? You're gonna prepare initial states for the probes, and you're gonna send it through the scattering map. You're gonna look at the statistics of correlations between the two algebras with operators localized in the processing regions, and you're gonna detect whether entanglement was harvested or not in the setup, right? So all that I said so far was pretty general, right? But in order to actually perform an explicit calculation, you have to have a model, a particular model within this framework to get some prediction. So that's exactly what was achieved in this recent paper by Rupp, where as a working hypothesis, he uses probe fields given by real free scalar fields that are then localized to the coupling regions. So yeah, the quantum field theory of the probes is given by, as I was saying, a free scalar field. So you can think of it as a smeared version of the usual quantum field theory phi of x, as we're used to seeing it, by some smearing function f that's going to be localized to the coupling region. And we can define a local mode of the field via quadrature operators that are obtained from the quantum field with some choices of smearing. And you can choose these compactly supported functions on the coupling region of interest such that these two operators commute to the identity. So that defines a single mode harmonic oscillator, which then gives you your probe. right? Then the initial state of each probe is chosen to be the restriction of a vacuum state or a generalization thereof, so a quasi-free state of the full free scalar field theory for each probe to the coupling region where they are defined. And with those ingredients, then Rueb was able to show that for any initial state of the two probes, there is a finite minimum value for the coupling constants that you need to have between the probes and the target system, the field of interest, such that you can actually harvest entanglement. So if the basically if the coupling is small enough, the final states of the probe, the final state of the probes will be separable, and that basically contradicts most of the literature that we know in relativistic information that deals with entanglement harvesting for basically arbitrarily small coupling. And the difference between these two setups is basically, as Rueb attributes it, he says that such threshold is due to the fact that for any state that you pick, for any physically reasonable state that you pick for the free scalar fields that are being chosen as the theory that models the probes, their restriction to some local region, in particular the coupling zones in this case, will lead to a mixed state, right? So, and that's due to a very general property of physically reasonable states in quantum field theory that's encoded by the Risch-Leader property. And yeah, that comes from the fact that for any Risch-Leader state, you're going to have entanglement between space-like separator regions, and therefore, if you restrict that to some local region, the reduced state is going to be mixed, right? So Rueb was able to show that in this toy model with localized modes of a free scalar field, but his claims, the nature of his claims, motivates investigations in a bit more detail on some aspects of these results. First, it is interesting to see exactly how mixed local modes of a free scalar field theory can be. And also, since at the end, the reason for this finite threshold for the coupling strength is due to the mixedness of the probes, you may wonder if this exact same effect can be mimicked or can be realized also in the typical UW detector models that we have, and they are so pervasive in relativistic quantum information. And those are exactly the questions that we addressed in our current work, and that's what we're going to be talking about next. So this is basically half of the talk. How am I doing in time?
Well, let's see.
Yeah. Okay, so next time, what I'm going to talk about is the results that we obtained from this work that can be summarized basically by saying that even though the mixedness of local modes of a free scalar field is always present, you can always make a clever choice of the shape of this mode such that you can achieve arbitrarily high purity. So without a stronger motivation for what particular choice of mode you're going to pick, the kinds of conclusions that you can draw from the Risch-Leader theorem are very limited. And also we're gonna see how within the usual framework of Unruh-DeWitt models or Unruh-DeWitt detectors, the exact threshold for mixedness, or conversely for the coupling strength that is needed for you to be able to harvest entanglement, can be computed in a very straightforward way. And with that, we're going to argue that the setups that we usually have at mind when talking about entanglement harvesting in realistic setups is actually safe from the problems that Rueb has raised. So yeah, that's it for now. I'm going to we're gonna talk about it next time.
All right, thank you very much. And as Bruno, please don't forget to come to the talk that will be also uploaded as a video next to this one. Are there any questions before we move to when we finish the meeting? All right, well, if there are no questions, then let's thank Bruno again. All right, and this is the end of the talk.